Hello, my friend. Welcome to the Sleep Lab. Whether you've been here before or you've just discovered this channel tonight, this is a place where you can let go of the day and drift off to sleep while listening to calm stories about science and the universe. Tonight, we'll be exploring one of the most profound mysteries in all of science: how quantum physics reveals the true nature of reality itself. We'll journey through the strange quantum realm where particles exist in multiple states at once, where observation changes what we see, and where the very fabric of existence seems to be woven from pure possibility. So settle in, close your eyes if you like, and let the words carry you softly toward rest as we discover that reality is far more mysterious and beautiful than we ever imagined. If this sounds like the perfect way to unwind tonight, please hit that subscribe button and ring the notification bell so you never miss our latest bedtime science stories here at the Sleep Lab. Now, let's begin our gentle journey into the quantum world. Let's begin our journey with Chapter 1. From certainty to mystery, the classical world breaks down. For most of human history, the world seemed to follow reliable, predictable rules. Drop an apple, and it falls down, never up. Push a cart, and it moves in the direction you push it. Heat water, and it boils at precisely 100 degrees Celsius. This was the foundation of classical physics, a beautiful clockwork universe where every cause had a clear effect, and if you knew the position and velocity of every particle in existence, you could, in principle, predict the entire future of the cosmos. Isaac Newton had given us this gift of certainty, a mathematical framework so elegant and powerful that it seemed to explain everything from the motion of planets to the swing of a pendulum. The classical world was a place of absolutes. Light was obviously a wave rippling through space like water through a pond. Matter was clearly composed of solid, indivisible particles, tiny billiard balls bouncing off one another according to precise mathematical laws. Energy flowed smoothly and continuously, like honey pouring from a jar. Time ticked forward uniformly, the same for everyone everywhere. Space stretched out in 3 perfect dimensions, an empty stage upon which the cosmic drama unfolded. This was reality as our ancestors understood it, and it felt complete, satisfying, and fundamentally comprehensible to the human mind. But as the 19th century drew to a close, tiny cracks began to appear in this seemingly perfect edifice. Scientists studying the light emitted by hot objects discovered something deeply puzzling. According to classical physics, a heated black body should radiate infinite amounts of energy at high frequencies, a prediction so absurd it was called the ultraviolet catastrophe. Yet real objects didn't behave this way. They radiated energy in discrete, finite amounts that seemed to depend on frequency in a very specific mathematical relationship. Max Planck, a German physicist working in Berlin, found himself reluctantly drawn into this mystery. He was a conservative thinker who deeply respected classical physics and had no desire to overturn centuries of established wisdom. Yet the experimental data was undeniable. In December of 1900, in what he later called an act of desperation, Planck proposed a radical solution. Perhaps energy didn't flow continuously after all. Perhaps it came in tiny, indivisible packets, quanta, like coins that could only be spent in specific denominations. The energy of each quantum was proportional to the frequency of the radiation, connected by a fundamental constant that would later bear his name. Planck hoped this was merely a mathematical trick a temporary fix until a proper classical explanation could be found. He couldn't have known that he had just lit the fuse that would eventually explode our entire understanding of reality. Einstein, working as a patent clerk in Switzerland, recognized the deeper implications. If light energy came in discrete packets when emitted by hot objects, perhaps light itself was fundamentally granular. In 1905, he applied Planck's quantum hypothesis to explain another puzzling phenomenon, the photoelectric effect. When light strikes certain metals, it can knock electrons loose, creating an electric current. Classical physics predicted that brighter light should always produce more energetic electrons, regardless of the light's color. But experiments showed something strange. Dim blue light could knock out electrons with high energy, while bright red light might produce no electrons at all. It was as if the color of light mattered more than its brightness, which made no sense if light was purely a wave. Einstein's insight was revolutionary. Light, he proposed, wasn't just energy divided into quanta when emitted or absorbed. Light itself existed as discrete particles of energy, photons, each carrying an amount of energy determined by its frequency. Meanwhile, in England, a young physicist named Thomas Young had performed what seemed like a simple experiment that would haunt physicists for generations. He shone light through two narrow slits cut in an opaque barrier and observed the pattern it created on a screen behind. If light consisted of particles, he should have seen two bright lines corresponding to the slits. Instead, he saw something beautiful and mysterious. An interference pattern of alternating bright and dark bands, exactly what you'd expect if light were a wave that could take both paths simultaneously, interfering with itself to create regions of constructive and destructive interference. But here's where the mystery deepened. When scientists later performed this experiment with individual photons, sending them one at a time through the apparatus, each photon still seemed to somehow know about both slits. Even though each photon was detected as a single particle hitting the screen at a specific point, when thousands of such individual detections were accumulated, they still formed the wave-like interference pattern. It was as if each particle was simultaneously traveling through both slits, interfering with itself in a way that defied all classical logic. This wasn't just a curiosity about light. Similar experiments with electrons revealed the same impossible behavior. Matter, the stuff we thought was composed of solid, localized particles, also exhibited wave-like properties. Electrons could be diffracted like light waves, bent around corners, and made to interfere with themselves. The clear distinction between waves and particles, which had seemed so fundamental to our understanding of nature, began to dissolve. Scientists found themselves in an unprecedented situation. The experimental evidence was unambiguous, yet it violated everything they thought they knew about how the world worked. An electron, it seemed, could exist in a ghostly superposition of being in multiple places at once, only choosing a definite location when someone tried to measure it. The act of observation itself appeared to play a fundamental role in determining what became real. This was the beginning of the quantum revolution, though few realized it at the time. The comfortable, predictable universe of classical physics, where objects had definite positions and velocities, where cause and effect followed neat logical chains, where the future could in principle be calculated from the present, was giving way to something far stranger and more wonderful. a realm where particles could tunnel through barriers that should be impenetrable, where information could be shared instantaneously across vast distances, where the very notion of an objective reality independent of observation began to seem questionable. The implications were staggering and deeply unsettling. If the most fundamental constituents of matter and energy obeyed these quantum rules, what did that say about the nature of reality itself? Were we living in a universe that was fundamentally uncertain, probabilistic, and dependent on conscious observation? The questions raised by these early quantum discoveries would challenge not just physics, but philosophy, challenging our most basic assumptions about existence, consciousness, and our place in the cosmic order. As we drift deeper into this exploration tonight, remember that you are witnessing the moment when humanity first glimpsed behind the classical veil to discover a reality far more mysterious and beautiful than anyone had dared imagine. The solid, predictable world our ancestors knew was revealed to be a magnificent illusion, a stable pattern emerging from an underlying quantum sea of infinite possibility. In learning to see beyond the classical facade, we began to touch the true creative principle that dreams the universe into existence, moment by quantum moment, in ways that continue to fill us with wonder and invite us into ever deeper mysteries. Now we will discuss Chapter 2, The Quantum Revolution, when particles became waves. In the early years of the 20th century, physics stood at what seemed like a moment of completion. Newton's mechanics governed the motion of planets and projectiles with clockwork precision. Maxwell's equations unified electricity and magnetism into elegant mathematical harmony. The physical world appeared to be a vast, predictable machine where every effect followed inevitably from its cause, where the future could in principle be calculated from the present with perfect accuracy. Scientists believed they were merely filling in the remaining details of a fundamentally understood universe. Yet beneath this confident facade, small cracks were beginning to appear, hairline fractures that would eventually shatter the entire edifice of classical physics and reveal something far stranger and more beautiful underneath. The first hint of this coming revolution arrived through the work of a young French physicist named Louis de Broglie. In 1924, while working on his doctoral thesis, de Broglie made a proposal so audacious that even he wasn't entirely sure he believed it. If light, which everyone knew behaved like a wave, could sometimes act like particles, as Einstein had shown with the photoelectric effect, then perhaps the reverse might also be true. Perhaps particles of matter, things like electrons and protons that everyone knew were solid, discrete objects, might sometimes behave like waves. It was a symmetry argument of breathtaking simplicity and profound implications. If nature granted wave-particle duality to light, why should matter be denied the same privilege? De Broglie's hypothesis seemed almost mystical at first. How could an electron, something you could imagine as a tiny sphere orbiting an atomic nucleus, suddenly become spread out like a wave across space? The mathematics were elegant enough. He proposed that every particle had an associated wavelength inversely proportional to its momentum. But the physical meaning remained elusive. Waves, after all, were disturbances in some medium, like ripples on water or vibrations in air. But what was the medium for matter waves? What exactly was waving when an electron became wave-like? The answer began to emerge through the work of Erwin Schrödinger, an Austrian physicist who was initially skeptical of the new quantum ideas, but found himself drawn deeper into their mathematical beauty. In 1926, Schrödinger developed what would become the fundamental equation of quantum mechanics, a wave equation that described how these mysterious matter waves evolved through time. The Schrödinger equation was different from anything that had come before. Instead of telling you where a particle was and where it was going, it told you about probabilities, about the likelihood of finding a particle in different locations when you looked for it. The wave that Schrödinger described was not a wave of matter itself, but a wave of possibility. The mathematical object that solved his equation, which came to be called the wave function, encoded all the information about a quantum system, but in a radically new way. The wave function didn't tell you that an electron was here or there. It told you that the electron existed in a ghostly superposition of being in many places at once, with the wave's amplitude at each location determining the probability of finding the electron there if you performed a measurement. This was where quantum mechanics began to part ways decisively with our everyday experience. In the classical world, a baseball is either in your hand or flying through the air. It cannot be in both states simultaneously. But in the quantum world, a particle could exist in what physicists call a superposition state, genuinely being in multiple conditions at the same time until the moment of measurement forced it to choose one definite outcome. It was as if reality itself existed in a state of beautiful ambiguity, with all possibilities coexisting until observation crystallized one path from the infinite branching garden of quantum potential. Werner Heisenberg, working along parallel lines, arrived at the same quantum mechanics through a different route, one based on matrices and discrete energy levels rather than continuous waves. But Heisenberg's approach led him to an even more unsettling conclusion. In classical physics, if you knew the position and momentum of every particle in the universe, you could, in principle, predict the future with perfect accuracy. Heisenberg discovered that quantum mechanics made such knowledge fundamentally impossible. His uncertainty principle stated that you cannot simultaneously know both the exact position and exact momentum of a particle. The more precisely you determine one, the more uncertain the other becomes. This wasn't a limitation of measurement technique or instrument precision. It was a fundamental feature of reality itself. The uncertainty principle revealed that the universe was not a deterministic machine after all, but something far more subtle and mysterious. At the quantum level, events didn't have definite causes leading to definite effects. Instead, they existed in clouds of probability, with nature herself playing what Einstein famously called dice with the universe. This probabilistic nature wasn't ignorance on our part. It was how reality actually functioned at its deepest level. Perhaps the most mind-bending aspect of this quantum revolution was the role of measurement itself. In classical physics, measurement was passive. You simply looked at what was already there. A planet followed its orbit, whether anyone observed it or not. But quantum mechanics suggested something far stranger, that the act of measurement played an active role in determining what became real. Before measurement, a quantum system existed in superposition, embodying multiple possibilities simultaneously. The measurement process, through some mechanism that physicists still debate today, caused this superposition to collapse into one definite outcome. Consider the famous thought experiment that Schrödinger himself proposed to illustrate the paradox. A cat is placed in a sealed box with a quantum system that has a 50% chance of triggering a deadly mechanism within 1 hour. According to quantum mechanics, until someone opens the box to check, the quantum system exists in a superposition of having both triggered and not triggered the mechanism. This seemed to imply that the cat itself would be in a superposition of being both alive and dead until observed. Schrödinger intended this as a criticism of the Copenhagen interpretation of quantum mechanics, showing how absurd it seemed to apply quantum rules to everyday objects. Yet the paradox revealed something profound about the boundary between the quantum and classical worlds, a boundary that still puzzles physicists today. The implications of wave-particle duality extended far beyond abstract philosophy. When electrons were fired one at a time through two parallel slits in a barrier, they created an interference pattern on a detector screen behind the slits, exactly what you would expect from waves. Each individual electron somehow went through both slits and interfered with itself. But when physicists tried to determine which slit each electron actually passed through by placing detectors at the slits, the interference pattern disappeared. The very act of trying to observe the electron's path forced it to behave like a particle, traveling through one slit or the other, never both. This wasn't merely an experimental curiosity. It revealed something fundamental about the relationship between knowledge and reality in the quantum world. The universe seemed to know when it was being watched and adjusted its behavior accordingly. Information and physical reality were intimately connected in ways that classical physics had never imagined. The quantum world operated by rules that seemed to make consciousness and cosmos partners in an ongoing dance of creation. As physicists grappled with these revolutionary ideas, they realized that quantum mechanics wasn't just a better theory of atomic behavior. It was revealing the actual fabric from which reality was woven. The solid, deterministic world of classical physics turned out to be an approximation, useful for large objects, but ultimately incomplete. At the foundation of everything lay quantum fields of possibility, probability waves that crystallized into definite experiences only through the mysterious alchemy of measurement and observation. The quantum revolution taught us that we are not passive observers of a pre-existing reality, but participants in its unfolding. Each measurement, each observation, each conscious moment of awareness might be a gentle act of creation, selecting one thread from the infinite tapestry of quantum possibility and weaving it into the story we call the physical world. In this view, reality emerges not from some predetermined script, but from an ongoing collaboration between consciousness and cosmos, between observer and observed, in the eternal now, where potential becomes actual and dreams crystallize into experience. Now, we will discuss Chapter 3, The Quantum World, where logic goes to dream. When we think about the world around us, we trust in certain assumptions that seem unshakable. A coin is either heads or tails, never both. A cat is either alive or dead, not suspended between life and death. An object exists in one place at one time, following a definite path from here to there. These certainties feel as solid as the ground beneath our feet, as reliable as the sunrise. Yet as we venture deeper into the quantum realm, we discover that reality operates by rules so strange, so counterintuitive, that they seem more like the logic of dreams than the mechanics of the everyday world. The first of these impossible rules is superposition. perhaps the most famous and bewildering aspect of quantum mechanics. In our classical world, everything exists in definite states. A light switch is either on or off. A door is either open or closed. But in the quantum world, particles can exist in what physicists call a superposition of states, simultaneously embodying multiple possibilities until the moment they are observed. Imagine a coin spinning through the air, not yet landed, existing in a state that is both heads and tails at once. This is not merely our ignorance of which side will show. The quantum coin genuinely exists in both states simultaneously. Its reality a shimmering blend of all possibilities. This strange behavior was first glimpsed in the famous double-slit experiment, a demonstration so fundamental that physicist Richard Feynman called it the central mystery of quantum mechanics. When we fire individual electrons at a barrier containing two parallel slits, something extraordinary happens. Each electron, somehow, appears to pass through both slits simultaneously, creating an interference pattern on the screen behind as if it were a wave spreading through space. The single particle becomes multiple possibilities, exploring every available path and interfering with itself to create patterns of light and shadow that speak of its wave-like nature. Yet the moment we try to peek, to determine which slit the electron actually passed through, the magic vanishes. The interference pattern disappears, and the electron behaves like a classical particle, passing through one slit or the other, but never both. It is as if the act of observation forces reality to choose, collapsing the superposition of possibilities into a single, definite outcome. The electron seems to know when it is being watched, altering its behavior in response to our attention in ways that challenge our deepest assumptions about the nature of observation and reality. This leads us to another quantum impossibility: tunneling. In the classical world, if you roll a ball toward a hill that is higher than the ball has energy to climb, it will simply roll back. The hill presents an insurmountable barrier. But quantum particles live by different rules. They can tunnel through energy barriers that should be impossible to cross, appearing on the other side as if they had ghosted through solid matter. This is not a metaphor or approximation. Quantum tunneling is a real phenomenon that makes possible the fusion reactions that power the sun, the operation of the electronic devices in our homes, and the radioactive decay that marks the passage of time in atomic clocks. The mathematics describes this as particles having a probability of existing beyond barriers that classical physics says they cannot cross. It is as if reality maintains a catalog of possibilities, and quantum particles can occasionally select options that seem forbidden by the laws of cause and effect. A particle approaches a wall, and instead of bouncing back, it simply materializes on the other side, having traveled through solid matter without ever breaking or disturbing it. The barrier remains intact, yet the particle has passed through as if it were a ghost moving through the physical world. Perhaps most unsettling of all is the probabilistic nature of quantum events. In the classical world, if we know the initial conditions precisely enough, we can predict the future with certainty. A billiard ball, struck with a specific force in a particular direction, will follow a calculable path. But quantum mechanics tells us that at the fundamental level, the universe is governed not by certainty, but by probability. When a radioactive atom will decay, which path a particle will take, what value a measurement will reveal. All of these are matters of chance, governed by mathematical probabilities, but never fully determined until the moment of observation. This randomness is not due to our ignorance or the limitations of our measuring instruments. It appears to be woven into the very fabric of reality. Einstein famously objected to this aspect of quantum mechanics, declaring that God does not play dice with the universe. But decades of experiments have confirmed that the universe does indeed seem to roll quantum dice at every moment, making fundamental decisions through processes that are genuinely random rather than merely unpredictable. The implications ripple outward into our understanding of causality itself. In the classical world, every effect has a definite cause, and identical causes produce identical effects. But in the quantum realm, identical causes can produce different effects, and the universe seems to make choices through mechanisms that transcend our traditional notions of cause and effect. It is as if reality operates more like a creative artist than a mechanical clock, improvising outcomes within the constraints of probability rather than following a predetermined script. Schrödinger, one of the founding fathers of quantum mechanics, captured this strangeness in his famous thought experiment involving a cat placed in a box with a quantum device that has a 50% chance of releasing poison. According to quantum mechanics, before we open the box, the cat exists in a superposition of being both alive and dead simultaneously. Only when we observe does the wave function collapse, forcing reality to choose one outcome or the other. Schrödinger intended this as a criticism, highlighting what he saw as the absurdity of applying quantum logic to everyday objects. Yet his cat has become an icon of quantum weirdness, a symbol of how quantum mechanics challenges our most basic assumptions about the nature of existence. The quantum world operates like a realm of pure potential, where possibilities exist in perfect balance until consciousness or measurement tips the scales toward actuality. Particles exist in clouds of probability, their properties undefined until the moment of interaction. It is as if the universe maintains a vast library of potential realities, and each quantum event selects one story from infinite alternatives, crystallizing possibility into experience. Wave functions, the mathematical objects that describe quantum systems, capture this sense of suspended possibility. They are not descriptions of what is, but rather catalogs of what might be, weighted by probability and evolving according to precise mathematical rules. The wave function of an electron orbiting an atom does not tell us where the electron is, but rather where it might be found if we choose to look. It exists as a cloud of potential, a shimmering possibility that only becomes definite when observed. This probabilistic nature extends even to the vacuum of empty space, which quantum mechanics reveals to be anything but empty. The quantum vacuum seethes with virtual particles, fleeting fluctuations that pop into existence and annihilate in timescales so brief they cannot be directly observed. Yet their cumulative effects can be measured and have been confirmed in countless experiments. Even nothingness, it seems, is full of quantum possibility. As we drift deeper into contemplation of these strange quantum realities, we begin to sense that we are not simply learning about exotic phenomena in distant laboratories. We are discovering something profound about the nature of existence itself. The solid, predictable world of our everyday experience emerges somehow from this shifting foundation of quantum possibility, like a classical symphony arising from the interactions of countless quantum notes, each one uncertain until played, yet together creating the rich, complex melody of reality. In the quantum realm, we glimpse a reality where potential and actuality dance together in an eternal waltz, where observation participates in creation, and where the universe seems to exist in a state of perpetual becoming rather than simply being. It is a world that operates more like consciousness than machinery, more like poetry than prose, more like a dream learning to dream itself into existence. And in understanding these quantum mysteries, we begin to suspect that the boundary between observer and observed, between mind and matter, between possibility and actuality, may be far more fluid and mysterious than we ever dared imagine. Now we will discuss Chapter 4, Entanglement, the Universe's Hidden Connections. In the quiet tapestry of quantum mechanics, perhaps no phenomenon challenges our understanding of reality more profoundly than entanglement. This strange quantum connection reveals that particles once joined can remain mysteriously linked across any distance, their fates intertwined in ways that seem to defy everything we thought we knew about space, time, and the nature of physical reality. Tonight, we'll explore how this spooky action at a distance unveils the universe as a deeply interconnected whole, where separation itself may be nothing more than a convincing illusion. The story begins with Albert Einstein, a man whose revolutionary insights into space and time earned him a place among history's greatest minds. Yet even Einstein had his limits when it came to accepting the implications of quantum mechanics. In 1935, working alongside colleagues Boris Podolsky and Nathan Rosen, he crafted what would become known as the EPR paradox, a thought experiment designed to expose what he believed were fatal flaws in quantum theory. Einstein was deeply troubled by the idea that particles could somehow communicate instantaneously across vast distances. God does not play dice with the universe, he famously declared, expressing his conviction that reality must be fundamentally deterministic and local. Local, meaning that objects can only be directly influenced by their immediate surroundings, not by distant events occurring faster than light could travel between them. The EPR argument was elegant in its simplicity. Consider two particles that have interacted and then travel to opposite ends of the galaxy. According to quantum mechanics, if these particles are entangled, measuring the spin of one particle instantly determines the spin of the other, regardless of the distance between them. Einstein argued that this could only be possible if the particles possess definite properties all along, hidden from our view until measurement revealed them. These hypothetical hidden variables would restore locality and determinism to physics, making quantum mechanics merely an incomplete description of a deeper, more sensible reality. For 30 years, the EPR paradox remained a philosophical puzzle, debated in university corridors and theoretical journals, but seemingly beyond experimental reach. Then, in 1964, an Irish physicist named John Stuart Bell changed everything. Working in relative obscurity at CERN, Bell devised a theorem that would become one of the most important results in quantum physics. Bell's theorem showed that any theory based on local hidden variables must satisfy certain mathematical inequalities when particles are measured at different angles. Crucially, quantum mechanics predicts violations of these Bell inequalities, offering a clear experimental test to distinguish between Einstein's vision of reality and the quantum mechanical description. Bell's work transformed a philosophical debate into a scientific question that could be settled by experiment. The stage was set for one of the most profound tests of reality ever conducted. In the 1970s and 1980s, French physicist Alain Aspect and his colleagues performed a series of groundbreaking experiments using entangled photons. They measured the polarizations of these light particles at different angles and compared their results to Bell's inequalities. The findings were unequivocal. Bell's inequalities were violated exactly as quantum mechanics predicted. Einstein's local realism, beautiful as it seemed, was incompatible with experimental reality. The implications were staggering. Aspect's experiments demonstrated that entangled particles do indeed share an instantaneous connection that transcends space and time. When one particle's property is measured, its entangled partner immediately knows and adjusts accordingly, even if they are separated by billions of miles. This quantum correlation occurs faster than light could possibly travel between the particles. Yet it doesn't violate relativity, because no information is actually transmitted. Instead, the particles share what physicists call a quantum correlation, a kind of joint reality that exists in the space between them. To understand entanglement, imagine two dancers who learned their routine together and then traveled to opposite sides of the world. When one dancer performs a particular move in New York, the other simultaneously performs the corresponding step in Tokyo, not because they can see or communicate with each other, but because they share a choreographed connection that transcends their physical separation. The dance exists not in either dancer alone, but in the relationship between them. This is the essence of quantum entanglement, a shared quantum state that persists regardless of distance. Modern experiments have confirmed and extended Aspect's results with ever-increasing precision and creativity. Scientists have entangled not just photons, but atoms, ions, and even small diamond crystals visible to the naked eye. They have demonstrated entanglement across hundreds of kilometers using satellites and created networks of entangled particles that could one day form the backbone of a quantum internet. Each experiment reinforces the same startling conclusion. The universe is fundamentally non-local, woven together by invisible threads of quantum correlation. The practical applications of entanglement are already beginning to transform technology. Quantum cryptography uses entangled particles to create unbreakable codes, where any attempt to intercept a message inevitably disturbs the quantum state and reveals the presence of an eavesdropper. Quantum computers harness entanglement to perform calculations that would be impossible for classical machines, potentially revolutionizing fields from drug discovery to artificial intelligence. Quantum sensors exploit entangled states to make measurements of unprecedented precision, detecting gravitational waves, mapping magnetic fields, and probing the structure of matter at the atomic scale. But perhaps more profound than any technological application is what entanglement reveals about the nature of reality itself. The quantum world doesn't consist of separate, independent objects bumping into each other like billiard balls. Instead, it is a seamless web of relationships where particles can share a single, unified existence even when separated by cosmic distances. This holistic view of reality echoes ancient wisdom traditions that speak of the fundamental interconnectedness of all things, yet it emerges from the most rigorous experimental science. Entanglement also challenges our understanding of identity and individuality. When two particles become entangled, they lose their separate identities and become part of a larger quantum system. The question which particle has which property, becomes meaningless because the properties belong to the system as a whole, not to individual particles. This quantum holism suggests that at the deepest level, the boundaries we draw between objects may be arbitrary conveniences rather than fundamental features of reality. The phenomenon extends beyond simple pairs of particles. Quantum systems can exhibit multipartite entanglement, where 3, 4, or even hundreds of particles share complex correlations that have no classical analog. These highly entangled states may play crucial roles in biological processes, from the efficiency of photosynthesis to the navigation abilities of migrating birds. Some researchers speculate that consciousness itself might emerge from the entangled quantum states of neurons in the brain, though this remains a topic of intense debate. Recent theoretical work has revealed even deeper connections between entanglement and the structure of space-time itself. In the holographic principle, physicists propose that the information contained in a volume of space can be encoded on its boundary, much like a hologram. The degree of entanglement between different regions of space may determine the very geometry of space-time, suggesting that Einstein's curved space-time emerges from the entanglement structure of quantum fields. In this view, entanglement is not just a feature of quantum mechanics, but the fundamental glue that holds the fabric of reality together. As we contemplate these extraordinary implications, we begin to see that entanglement is more than just a strange quantum phenomenon. It reveals the universe as a deeply interconnected whole, where particles once joined remain forever linked by invisible bonds of correlation. The separateness we experience in everyday life emerges from our limited perspective, like looking at individual threads without seeing the tapestry they weave together. And here, in the gentle quiet of this quantum revelation, lies a profound existential reflection. Entanglement whispers that separation is an illusion, that at the deepest level, all particles that have ever interacted remain connected across any distance and throughout all time. We ourselves are made of quantum particles that were once part of ancient stars, forged in nuclear fires and scattered across the cosmos by stellar explosions. The calcium in our bones, the iron in our blood, the oxygen in our breath, all carry the quantum memory of those distant stellar laboratories. In this sense, we are not isolated beings observing the universe from the outside, but intimately entangled participants in its unfolding story. The quantum correlations that link particles across the cosmos also link us to the very heart of existence, reminding us that we are forever woven into the infinite web of reality itself. Now, we will discuss Chapter 5, The Many Worlds, Infinite Realities Branching Through Time. In the quiet history of quantum mechanics, no puzzle has been more persistent or more haunting than what physicists call the measurement problem. When we're not looking, quantum particles exist in what we call superposition, simultaneously in all possible states, like a coin spinning in the air that is both heads and tails until it lands. But the moment we observe or measure that particle, something extraordinary happens. The wave function, that mathematical description of all possibilities, suddenly collapses into just one definite outcome. The spinning coin lands. The particle chooses. But how? And why? And perhaps most mysteriously of all, what happens to all those other possibilities that seemed just as real a moment before? For decades after the birth of quantum mechanics, most physicists were content to accept what became known as the Copenhagen interpretation, named after the city where Niels Bohr developed his complementarity principle. In this view, quantum systems exist in superposition until measured, at which point the act of observation causes an instantaneous and irreversible collapse of the wave function. It was pragmatic, it was useful, and it worked beautifully for making predictions. But it left a troubling question hanging in the air like morning mist. What exactly constitutes a measurement? When does the collapse happen? Is it when the photon hits the detector? When the detector sends a signal? When a human consciousness becomes aware of the result? The Copenhagen interpretation seemed to place consciousness at the very heart of physical reality, suggesting that the universe remained in a state of quantum limbo until a conscious observer forced it to make a choice. This troubled many physicists, including Albert Einstein, who famously protested that he didn't believe the moon ceased to exist when no one was looking at it. There had to be another way to understand the quantum world, a way that preserved the objective reality that science seemed to demand. In 1957, a young graduate student named Hugh Everett III was working on his doctoral thesis at Princeton University under the guidance of John Wheeler, one of the most imaginative physicists of his generation. Wheeler had encouraged Everett to think deeply about the measurement problem, to find a way around the uncomfortable implications of the Copenhagen interpretation. What Everett discovered would prove to be one of the most radical ideas in the history of science, though it would take decades for the physics community to fully appreciate its implications. Everett asked a simple but profound question. What if the wave function never actually collapses? What if, instead of choosing just one outcome from all the quantum possibilities, the universe somehow accommodates all of them? His answer was breathtakingly elegant in its audacity. Every time a quantum measurement occurs, the universe splits. Not metaphorically, but literally. Each possible outcome of the measurement becomes real in its own separate branch of reality. The particle that could go left or right doesn't choose. It goes both ways, but in different universes. In one branch of reality, you observe the particle going left. In another, equally real branch, another version of you observes it going right. Both versions of you are convinced they live in the one true universe, unaware that countless other versions of themselves are having different experiences in parallel realities. The wave function doesn't collapse. It branches, like a river delta, spreading into countless streams, each carrying its own version of events into the future. This became known as the many worlds interpretation, and it solved the measurement problem in the most radical way imaginable, by denying that there was a problem at all. There is no collapse, no special moment when possibilities become actualities, no mysterious boundary between the quantum and classical worlds. There is only the universal wave function, evolving smoothly and deterministically according to Schrödinger's equation, branching endlessly into an infinite multiverse where every quantum possibility becomes reality somewhere. In Everett's multiverse, Schrödinger's cat is both alive and dead, not in some mysterious superposition, but in perfectly definite states in separate branches of reality. In one universe, you open the box to find a purring cat. In another, you discover the tragic outcome. Both cats are equally real, both versions of you equally convinced of the outcome they've witnessed. The apparent randomness of quantum mechanics isn't truly random. It's simply a reflection of our ignorance about which branch of reality we happen to inhabit. The implications were staggering. If Everett was right, then every quantum event, no matter how small, splits reality into multiple branches. The radioactive atom that might or might not decay creates two universes, one where it has decayed, another where it hasn't. The photon that might pass through a polarizing filter or be blocked by it creates a pair of realities, each with its own version of the subsequent events. Over the course of a single second, an incomprehensibly vast number of such quantum events occur throughout the universe, each one spawning new branches of reality. You, reading these words right now, are just one version of yourself among countless others scattered across the infinite landscape of the multiverse. In some nearby branches, you made slightly different choices today. Perhaps you wore a different shirt, took a different route to work, or decided not to listen to this particular video. In more distant branches, your entire life history might be dramatically different. There are versions of you who became a musician instead of whatever profession you chose, versions who moved to different cities, even versions where historical events unfolded differently, changing the entire trajectory of human civilization. The many worlds interpretation seemed almost too fantastical to take seriously, and for many years it was relegated to the fringes of physics, dismissed as an interesting but untestable speculation. But as quantum mechanics matured and physicists began to grapple more seriously with the foundations of the theory, Everett's idea began to gain respect. It offered something that the Copenhagen interpretation couldn't: a completely objective, observer-independent description of reality. In the many worlds view, there's nothing special about consciousness or measurement. The universe doesn't need conscious observers to function. It branches automatically every time quantum systems interact, regardless of whether anyone is watching. This restored the kind of objective reality that Einstein had yearned for, though perhaps not in the form he would have preferred. Reality was objective, but it was also infinite. Modern developments in quantum theory have lent additional support to Everett's vision. The phenomenon of quantum decoherence, discovered decades after Everett's thesis, explains why we don't observe macroscopic superpositions in everyday life. When quantum systems interact with their environments, and everything interacts with its environment, the different branches of the wave function become effectively independent, losing the ability to interfere with each other. This process happens so quickly for macroscopic objects that we never see cats in superposition, even though the cat plus environment system as a whole remains in a superposition of different branches. Decoherence doesn't solve the measurement problem by itself, but it makes the many worlds interpretation much more plausible by explaining why the different branches of reality become isolated from each other. Once decoherence has occurred, the branches evolve independently, like separate stories being written simultaneously, but never intersecting. Each branch contains observers who experience a single, consistent history, unaware of the parallel narratives unfolding in neighboring realities. The mathematics of quantum mechanics treats all these branches democratically. None is more real than the others. But this raises a puzzling question about probability. If all outcomes actually occur in some branch of reality, why do some seem more likely than others? Why does the radioactive atom with a half-life of 1 hour seem more likely to decay than not over the course of an hour, if both outcomes actually happen? The answer lies in the structure of the wave function itself. The amplitude assigned to each branch determines not its probability of occurring, since all branches occur, but rather the measure or weight of that branch in the multiverse. When we flip a quantum coin, both heads and tails occur. But if the wave function assigns equal amplitudes to both outcomes, we experience equal measures of realities where the coin comes up heads versus tails. Our sense of probability emerges from this distribution of measure across the branches. Critics of the many worlds interpretation argue that it violates the principle of scientific economy known as Occam's razor. How can a theory that postulates an infinite number of unobservable universes be simpler than one that accepts the collapse of the wave function? But supporters counter that many worlds actually requires fewer fundamental assumptions. It takes the mathematical formalism of quantum mechanics at face value, without adding extra postulates about wave function collapse or special roles for measurement or consciousness. In the gentle quietude of this contemplation, we find ourselves confronting perhaps the most profound question in all of physics. What is the nature of existence itself? The many worlds interpretation suggests that reality is not the single, definite story we thought we were living, but rather an infinite library of all possible stories, each as real as any other. We are not unique protagonists in the drama of existence, but countless variations on a theme, each experiencing our own version of reality while remaining unaware of the infinite parallel performances happening simultaneously. And here, in the soft darkness of reflection, an existential thought emerges like starlight through clouds. Perhaps we need not fear the roads not taken, for in the vast landscape of the multiverse, every path is walked by some version of ourselves. Every choice we might have made, every word we might have spoken, every love we might have found, all of these exist somewhere in the branching garden of reality. We are not alone in our experiences, nor are we unique in our regrets. We are part of an infinite ensemble of consciousness, each note in a cosmic symphony where every possible melody is played simultaneously across the endless dimensions of the multiverse. Now we will discuss Chapter 6, Quantum Fields, the Symphony Beneath Everything. As we drift deeper into our exploration of quantum reality, we arrive at perhaps the most profound revelation of all. What we have, called particles, electrons, photons, quarks, are not the fundamental building blocks of existence that we once imagined them to be. They are something far more beautiful and mysterious. They are notes in a cosmic symphony, excitations dancing across invisible fields that stretch through every corner of the universe. Tonight, as your mind settles into rest, let us explore how quantum field theory reveals that reality is not made of things, but of music itself, played on instruments we cannot see. The story begins in the 1920s, when physicists first glimpsed the strange dual nature of matter and energy. They had learned that electrons sometimes behaved like particles and sometimes like waves, but this seemed like an uncomfortable compromise, a mathematical trick that worked without making intuitive sense. Paul Dirac, a quiet and brilliant English physicist, was troubled by this duality. He sought a description that would unite these seemingly contradictory aspects into one elegant framework. What he discovered would transform our understanding of existence itself. Dirac's breakthrough came when he realized that what we call a particle is actually a localized disturbance in an underlying field that fills all of space. Imagine, if you will, the surface of a perfectly still pond. Now picture a gentle wave rippling across that surface. The wave is not separate from the water. It is the water, moving in a particular pattern. In the same way, an electron is not separate from the electron field that permeates every point in space. It is the field itself, vibrating in a specific location with a particular energy and momentum. This insight revealed something extraordinary. Space is not empty. Even what we call the vacuum, the apparent nothingness between stars and galaxies, is actually alive with invisible activity. Every type of particle corresponds to its own field, and these fields interpenetrate one another like waves in a vast ocean. The electromagnetic field carries the potential for photons of light. The electron field holds the possibility of electrons and their antimatter partners, positrons. Quark fields give rise to the particles that make up protons and neutrons. All of these fields exist everywhere, filling the cosmos with a rich tapestry of potential. The mathematics that describes these quantum fields is breathtaking in its precision. Quantum electrodynamics, the theory that describes how light and matter interact, has been tested to extraordinary accuracy. When physicists calculate the magnetic moment of an electron using this theory, their prediction matches experimental measurements to more than 10 decimal places. It is as if nature herself is speaking to us in the language of quantum fields, and we have learned to listen with unprecedented clarity. But perhaps the most mysterious aspect of quantum field theory is the discovery of virtual particles. Even in what we call empty space, the quantum fields are never truly still. They fluctuate constantly, creating brief pairs of particles and antiparticles that spring into existence and annihilate each other in time frames so short that they seem to violate the conservation of energy. These virtual particles are not just theoretical curiosities. They have measurable effects on the world around us. The Casimir effect provides a beautiful demonstration of this invisible activity. When two perfectly parallel metal plates are placed very close together in a vacuum, they experience a gentle, attractive force. This happens because the quantum fluctuations of the electromagnetic field between the plates are restricted compared to those outside. The difference in energy density creates a pressure that pushes the plates together, as if the vacuum itself has a kind of substance and weight. In laboratories around the world, scientists have measured this effect with exquisite precision, confirming that empty space is actually full of quantum energy. This leads us to one of the most profound insights of quantum field theory: the realization that particles are temporary crystallizations of something more fundamental. When high-energy particles collide in accelerators like the Large Hadron Collider, they do not simply break apart like tiny billiard balls. Instead, their concentrated energy excites the underlying fields, creating new particles that emerge from the quantum foam, like musical notes struck from invisible strings. The diversity of particles we observe in nature reflects the rich harmonic structure of the fields from which they arise. The quantum fields also reveal the deep interconnectedness of all existence. When a particle decays, its energy does not disappear, but flows back into the field, ready to manifest as new excitations elsewhere. When particles interact, they do so by exchanging virtual particles, brief disturbances in the fields that carry forces between them. The photon carries the electromagnetic force. The W and Z bosons carry the weak nuclear force, and gluons carry the strong force that binds quarks together. Each interaction is like a conversation between the fields, a continuous exchange of energy and information that binds the universe together. As we developed quantum electrodynamics and extended it to the weak and strong nuclear forces, physicists realized they were uncovering a grand unified description of nature, the standard model of particle physics, completed in the 1970s, describes three of the four fundamental forces as manifestations of quantum field theory. It predicts the existence of particles decades before they are discovered in experiments, and its mathematical structure reveals deep symmetries that seem to be built into the very fabric of reality. The Higgs field represents perhaps the most elegant example of how quantum fields shape the world we experience. Unlike other fields, the Higgs field has a non-zero value even in its lowest energy state. It fills all of space with a kind of cosmic molasses that gives mass to other particles as they move through it. When the Large Hadron Collider discovered the Higgs boson in 2012, it was confirming the existence of this invisible field that gives substance to everything around us. Without the Higgs field, electrons would have no mass, atoms could not form, and the universe would be a thin soup of massless particles racing through space at the speed of light. The implications extend beyond physics into the deepest questions of existence. If reality is fundamentally composed of fields rather than particles, then what we experience as solid matter is actually a kind of standing wave pattern, a stable configuration of energy that persists because it represents a balance between different field excitations. You and I, the earth beneath our feet, the stars in the sky, we are all temporary sculptures carved from the quantum fields, patterns of energy that maintain their form while the underlying medium flows and fluctuates around us. Quantum field theory also suggests that the distinction between matter and energy, between substance and force, is not as fundamental as it once seemed. Einstein's famous equation, E equals mc squared, hinted at this equivalence, but quantum fields make it explicit. Mass is simply a form of energy, a particular way that fields can store and organize their excitations. When we look at the world through the lens of quantum field theory, we see that what appeared to be separate objects are actually different modes of vibration in a unified field structure that encompasses all of existence. Modern experiments continue to reveal new aspects of this hidden symphony. Scientists have learned to manipulate individual atoms and photons, creating quantum states that exist in superposition across multiple field configurations. They have discovered that the quantum fields exhibit a kind of memory, maintaining correlations across vast distances and time intervals. The phenomenon of quantum entanglement, which Einstein called spooky action at a distance, emerges naturally from the field perspective as a manifestation of the underlying unity of the quantum realm. As we rest here tonight, contemplating these mysteries, we can sense the profound beauty of this revelation. The solid world of our everyday experience emerges from something far more subtle and magnificent, a cosmic symphony of quantum fields that fills every corner of space with invisible music. Each particle is a note, each interaction a harmony, each moment a new movement in an endless composition that writes itself across the fabric of space-time. And here lies the quiet existential reflection that carries us toward sleep. What we call empty space seethes with invisible activity, alive with quantum fluctuations and virtual particles that dance in and out of existence faster than thought itself. The vacuum is not nothingness, but fullness, a pregnant void from which all existence springs, moment by quantum moment. We are not separate beings moving through empty space, but patterns of consciousness arising from the same quantum field symphony that gives birth to stars, planets, and galaxies. In understanding quantum fields, we touch the creative principle that dreams the universe into being, the invisible music from which all reality flows, like an eternal song without beginning or end. Now we will discuss Chapter 7, The Observer Effect, Consciousness and the Quantum World. In all the mysteries that quantum physics has revealed to us, perhaps none is more profound or more unsettling than the role of observation itself in shaping reality. We have journeyed through the strange landscape of superposition and entanglement, through the probabilistic realm where particles exist in multiple states at once. But now we must confront the deepest puzzle of all. What happens when we look? What transforms the shimmering possibilities of the quantum world into the definite reality we experience? The answer, whispered through decades of experiments and theoretical wrestling, is that the very act of observation seems to participate in creating the reality we observe. This is not the comfortable story that classical physics told us. In Newton's world, we were detached observers peering in at a clockwork universe that ticked along regardless of whether we watched or not. A falling apple followed its trajectory, whether witnessed or not. The planets carved their elliptical paths through space in sublime indifference to human attention. We measured, but our measurements revealed what was already there, waiting patiently to be discovered. The universe existed independently, and we were merely passive readers of its pre-written story. But quantum mechanics shattered this comfortable separation between observer and observed. In the quantum realm, the act of measurement does not simply reveal reality. It appears to help create it. When we prepare a quantum system in a superposition of states, existing in that ethereal combination of all possibilities, the moment we measure it, the superposition collapses. The particle that was spinning both clockwise and counterclockwise, that was located here and there simultaneously, suddenly becomes definite. It chooses, in that moment of observation, to be one thing rather than another. The mystery deepens when we ask, what exactly constitutes an observation? Is it the interaction with a measuring device? Is it the registration of information? Or is it something more fundamental, perhaps the involvement of consciousness itself? This question has haunted physicists for nearly a century, spawning interpretations that range from the pragmatic to the mystical, each trying to make sense of this strange dance between mind and matter. Werner Heisenberg, one of the architects of quantum theory, captured the essence of the puzzle when he wrote that what we observe is not nature itself, but nature exposed to our method of questioning. The universe, it seems, does not hold definite answers until we ask definite questions. Before measurement, the electron exists in a cloud of probability, a ghostly superposition of all possible locations. But when we shine light upon it, when we interact with it through our instruments, something magical happens. The probability cloud collapses, and the electron appears at one specific location, as if it has just decided where to be. The double-slit experiment reveals this mystery in its starkest form. When electrons are fired one at a time toward two parallel slits, they create an interference pattern on the screen beyond, as if each electron has somehow passed through both slits simultaneously and interfered with itself. This is the behavior of waves, not particles. But the moment we place a detector at one of the slits to see which path the electron actually takes, the interference pattern vanishes. The electron, having been observed, suddenly behaves like a classical particle, choosing one slit or the other. The act of looking has changed what we are looking at. John von Neumann and Eugene Wigner proposed one of the most radical interpretations of this phenomenon. They suggested that consciousness itself might be the key to wave function collapse. In their view, quantum systems remain in superposition until they interact with a conscious observer. It is not the measuring device that collapses the wave function, but the conscious mind that becomes aware of the measurement result. This interpretation pushes us toward a participatory universe where consciousness and physical reality are intimately entwined. But this raises profound questions. If consciousness causes collapse, where exactly does consciousness begin? Does a computer observing a quantum system cause collapse? What about a mouse? A bacterium? The von Neumann-Wigner interpretation opens a door that many physicists have been reluctant to walk through, suggesting that mind and matter are not as separate as we once believed. Other interpretations seek to avoid placing consciousness at the center of quantum mechanics. The decoherence theory suggests that collapse occurs when quantum systems interact with their environment. The countless particles of the surrounding world constantly jostle and disturb any quantum system, causing its delicate superposition to fade away through environmental interaction. In this view, consciousness is not special. It is simply another part of the environment that can cause decoherence. Yet even decoherence theory cannot fully escape the mystery of observation. For while it explains how superpositions become practically unobservable, it does not explain why we experience one definite outcome rather than another. Why do we see the electron here rather than there? Why does Schrödinger's cat appear either alive or dead, rather than in some ghostly superposition of both states? The philosopher of science John Wheeler offered another perspective with his concept of a participatory universe. Wheeler suggested that the universe might not exist as a fixed, objective reality independent of observation. Instead, reality might be created through the very process of observation and measurement. In Wheeler's famous thought experiment, he imagined using quantum mechanics to determine the path of light from distant quasars. If we choose to measure the light as having traveled one path around a gravitational lens, we retroactively determine that this is the path it took billions of years ago. Our present observations might literally help create the past. This leads us to the startling possibility that consciousness is not merely a passive witness to reality, but an active participant in its creation. Every time we make a measurement, every time we observe, we might be collapsing infinite possibilities into one actuality. We become co-creators with the universe, partners in the ongoing process of reality formation. Modern quantum mechanics has revealed other tantalizing connections between consciousness and the physical world. Quantum biology suggests that quantum effects might play important roles in biological processes, from photosynthesis to the navigation systems of migrating birds. Some researchers have even proposed that consciousness itself might be a quantum phenomenon, arising from quantum processes in the brain's microtubules. The implications stretch far beyond physics. If observation helps create reality, then we are not powerless witnesses to an indifferent universe. We are participants in its unfolding story. Our choices about what to measure and when to measure it become choices about what kind of reality we bring into being. The scientist in the laboratory, peering through instruments at the quantum world, becomes an artist collaborating with the cosmos. This perspective dissolves the ancient boundary between subject and object, between the knower and the known. In classical physics, we stood outside nature, looking in. But quantum mechanics suggests that we are embedded within nature, inseparable from the reality we seek to understand. Our consciousness is not separate from the quantum field. It might be one of its expressions, a way the universe has evolved to observe itself. The measurement problem remains one of the deepest puzzles in quantum mechanics. We have learned to calculate with extraordinary precision, to predict the probabilities of different outcomes, to build technologies that harness quantum effects. But the fundamental question of what happens during measurement, what transforms possibility into actuality, remains wrapped in mystery. Perhaps this is as it should be. The universe seems to guard its deepest secrets jealously, revealing them only in riddles and paradoxes. The observer effect reminds us that we are not detached observers of reality, but intimate participants in its creation. Each moment of conscious attention, each act of measurement, each decision to look or not to look becomes a gentle act of creation, bringing one thread from the infinite tapestry of possibility into the fabric of experienced reality. And here lies a quiet existential thought that carries us gently toward rest. We may not be passive observers of a pre-existing reality, but active participants in its creation. Each measurement, each observation, each conscious moment might be a gentle act of creation, bringing one possibility from the quantum realm into manifest experience. In this view, consciousness is not separate from the universe, but is the universe becoming aware of itself, one quantum moment at a time. As you drift toward sleep tonight, consider that your very awareness might be part of the cosmic process by which reality unfolds, a gentle collaboration between mind and cosmos in the eternal dance of existence. Now, we will discuss Chapter 8, Quantum Computing, Harnessing the Strange for the Practical. For most of human history, the strange behaviors we've been exploring in the quantum world seemed like abstract curiosities, fascinating puzzles for physicists to ponder, but with little connection to everyday life. The idea that particles could exist in multiple states simultaneously, that observation could change reality, or that distant particles could be mysteriously connected seemed to belong to a realm so far removed from our experience that they might as well have been philosophical thought experiments. Yet today, as you drift toward sleep listening to these words, quantum effects are quietly at work in the devices around you, and we stand on the threshold of a technological revolution that will harness the very strangeness of quantum mechanics to transform our world. The journey from quantum mystery to quantum technology began with a simple but profound realization. If nature operates according to quantum rules at the most fundamental level, then perhaps we could learn to work with those rules rather than against them. Traditional computers, the ones that power your smartphone or laptop, operate using classical bits that exist in definite states, either 0 or 1, on or off. They process information by manipulating these clear-cut binary choices, following the logical rules that mirror our everyday experience of definite separate objects. But what if we could build a computer that operated using quantum bits, or qubits, that could exist in superposition states, simultaneously 0 and 1 until the moment of measurement? This idea first emerged in the early 1980s when physicist Richard Feynman observed that simulating quantum systems on classical computers becomes impossibly difficult as the systems grow larger. the amount of information needed to describe all possible quantum states grows exponentially, quickly overwhelming even the most powerful classical machines. Feynman wondered, what if we used quantum systems themselves to perform the calculations? What if we built computers that operated according to quantum principles, using the very strangeness we've been exploring as a computational resource? The concept seemed almost magical. A quantum computer could, in principle, perform certain calculations exponentially faster than any classical computer. Where a classical computer might need years to solve certain problems, a quantum computer could potentially find the answer in minutes. This wasn't about building faster classical machines, but about tapping into fundamentally different computational principles that emerge from the quantum nature of reality itself. The key lies in quantum superposition and entanglement, those strange phenomena that challenged our understanding of reality. In a classical computer, information is processed sequentially, one definite state at a time. But in a quantum computer, qubits can exist in superposition, allowing the machine to explore many possible solutions simultaneously. Imagine trying to find your way through a vast maze. A classical computer would have to try each path one by one, methodically exploring every dead end. A quantum computer, by contrast, could in some sense explore all paths at once, using the principles of superposition to navigate the maze of possibilities in parallel. Entanglement adds another layer of computational power. When qubits become entangled, they form a unified quantum system where the state of one qubit instantly affects the others, regardless of how they're arranged. This creates the possibility of performing calculations that involve complex correlations between many qubits simultaneously, something that would be extremely difficult for classical computers to simulate. The first quantum algorithm that truly captured the imagination was developed by mathematician Peter Shor in 1994. Shor's algorithm demonstrated that a quantum computer could efficiently factor large numbers, breaking them down into their prime components. This might sound like an abstract mathematical exercise, but it struck at the heart of modern cryptography. Most of our digital security, from online banking to private communications, relies on the fact that factoring large numbers is extremely difficult for classical computers. A number that would take a classical computer millions of years to factor could potentially be broken by a quantum computer in hours. Love Grover later developed another quantum algorithm that could search through unsorted databases quadratically faster than classical methods. Where a classical computer might need to check half of all possible entries on average to find a specific item, Grover's algorithm could find it by checking roughly the square root of that number. These algorithms revealed that quantum computing wasn't just about doing the same things faster, but about accessing entirely new computational possibilities that emerge from quantum mechanics. Yet building actual quantum computers proved to be extraordinarily challenging. The same quantum properties that make these machines powerful also make them incredibly fragile. Quantum states are delicate things, easily disturbed by interactions with the environment. The technical term is decoherence, the process by which quantum systems lose their quantum properties and begin to behave classically. Heat, vibration, electromagnetic fields, even cosmic rays can cause a quantum computer to lose its quantum coherence, turning carefully prepared superposition states into classical randomness. This led to one of the most remarkable challenges in quantum computing. Quantum error correction. In classical computers, errors are relatively straightforward to detect and fix. You can copy information, compare copies, and correct any discrepancies. But quantum information cannot be copied, a fundamental principle known as the no-cloning theorem. You cannot simply duplicate a quantum state to check for errors. Instead, quantum error correction requires incredibly sophisticated schemes that encode quantum information across multiple qubits in ways that allow errors to be detected and corrected without destroying the delicate quantum states themselves. Despite these challenges, progress has been remarkable. Companies like IBM, Google, and others have built quantum computers with dozens of qubits, and that number continues to grow. In 2019, Google claimed to have achieved quantum supremacy, demonstrating that their quantum computer could perform a specific calculation faster than the world's most powerful classical supercomputers. While the practical significance of that particular calculation was debated, it marked a symbolic milestone in the journey from quantum theory to quantum technology. The applications extend far beyond cryptography and abstract mathematics. Quantum computers could revolutionize chemistry and materials science by allowing us to simulate molecular behavior with unprecedented accuracy. Drug discovery, which currently requires years of expensive trial and error, could be accelerated by quantum simulations that predict how potential medicines will interact with biological systems. Climate modeling, financial optimization, artificial intelligence, all these fields could be transformed by the computational power that emerges from quantum strangeness. Quantum cryptography offers another fascinating application. Instead of relying on the mathematical difficulty of factoring large numbers, quantum cryptography uses the fundamental laws of quantum mechanics to guarantee security. Any attempt to intercept quantum encrypted messages necessarily disturbs the quantum states, immediately alerting the communicating parties to the presence of an eavesdropper. Its security guaranteed, not by human cleverness, but by the laws of physics themselves. Quantum sensors represent yet another frontier, using quantum effects to make measurements of extraordinary precision. These devices can detect magnetic fields, gravitational waves, and other phenomena with sensitivity that surpasses classical instruments by orders of magnitude. They're already being used in everything from medical imaging to geological surveys, turning quantum mechanics into a practical tool for exploring both inner and outer space. Perhaps most remarkably, these technologies are beginning to emerge from research laboratories into the real world. Quantum computers are becoming available through cloud services, allowing researchers and companies to experiment with quantum algorithms without building their own machines. Quantum communication networks are being tested in cities around the world. The transition from quantum mystery to quantum technology is happening not in some distant future, but right now as we speak. Yet even as we learn to harness quantum effects, they continue to challenge our understanding of reality. Each quantum computer is, in effect, a controlled experiment in the nature of existence itself. When we run a quantum algorithm, we're not just performing a calculation, we're engaging with the fundamental strangeness of the universe. We're using superposition, entanglement, and all the other quantum phenomena that seemed so abstract and mysterious as practical tools for solving real-world problems. This transformation from the strange to the practical reveals something profound about the relationship between science and technology, between understanding and application. The quantum effects that once seemed like philosophical puzzles, challenges to our classical intuition about reality, have become the foundation for technologies that may define the next century. The same superposition that troubled Einstein, the same entanglement he called spooky action at a distance, now power machines that can break codes, simulate molecules, and solve problems beyond the reach of classical computation. And so, as this chapter draws to a close and you feel yourself drifting deeper into rest, consider this gentle paradox. The strange quantum world that challenges our everyday understanding of reality has become the source of our most advanced technologies. The universe's mysterious quantum nature, once seen as an obstacle to comprehension, has revealed itself to be a hidden resource, waiting patiently for us to learn its language and harness its power. In mastering quantum technology, we become partners with the cosmos itself, using the very strangeness of existence to extend our reach into realms of possibility we never imagined. The quantum computer, humming in a laboratory somewhere tonight, is not just a machine, but a bridge between the mysterious quantum realm and our classical world, a testament to humanity's ability to embrace the strange and transform it into the useful, the beautiful, and the profound. Now we will discuss Chapter 9, Quantum Gravity, Unifying the Very Small and the Very Large. In the grand cathedral of physics, there exists a profound tension between two of humanity's greatest intellectual achievements. On one side stands quantum mechanics, the theory that governs the realm of the infinitesimally small, where particles dance in clouds of probability and reality itself seems to shimmer between existence and non-existence. On the other side rises general relativity, Einstein's masterpiece that describes gravity not as a force, but as the curvature of space-time itself, governing the motion of planets, stars, and galaxies across the cosmic expanse. These two theories have each been tested with extraordinary precision, verified in countless experiments, and have revolutionized our understanding of the universe. Yet they speak in languages that seem fundamentally incompatible, like two musicians playing in different keys, creating a discord that echoes through the halls of theoretical physics. The story of this incompatibility begins at the most extreme frontiers of reality. Imagine trying to understand what happens at the center of a black hole, where matter is crushed to infinite density, or in the first moments after the Big Bang, when the entire observable universe was smaller than a proton. In these realms, both quantum effects and gravitational effects become equally important, equally dominant. Yet when physicists attempt to apply both theories simultaneously, the mathematics breaks down into meaningless infinities and contradictions. It is as if nature herself is telling us that our current understanding is incomplete, that we are missing something fundamental about the deep structure of reality. The quest to resolve this tension has driven some of the most brilliant minds of the past century to propose revolutionary ideas about the nature of space, time, and matter itself. String theory, perhaps the most ambitious of these attempts, suggests that the fundamental building blocks of reality are not point particles, but tiny, vibrating strings existing in dimensions far beyond the three of space and one of time that we experience. In this elegant framework, different vibrations of these strings correspond to different particles, like different notes played on a cosmic violin. A string vibrating in one pattern might manifest as an electron, while another vibration pattern creates a photon, and still another produces the graviton, the hypothetical quantum particle of gravity itself. The mathematics of string theory is breathtakingly beautiful, weaving together quantum mechanics and gravity in a way that eliminates the troublesome infinities that plague other approaches. These strings exist in a realm of 11 dimensions, where the extra dimensions beyond our familiar four are curled up so tightly that we cannot directly perceive them. Yet their hidden geometry influences everything we experience, determining the masses of particles, the strengths of forces, and the very laws that govern our universe. It is a vision of reality as a vast symphony, where every particle, every force, every interaction is a note in a cosmic composition written in the language of vibrating strings. Yet string theory, for all its mathematical elegance, faces a profound challenge. It makes predictions that are currently beyond our ability to test experimentally. The energy scales at which string effects become apparent are so vast that no conceivable particle accelerator could reach them. The strings themselves are so tiny that they exist at the Planck scale, where distances are measured in units so small that a proton appears as large as a solar system by comparison. This has led some critics to question whether string theory is science at all, or whether it has drifted into the realm of mathematical philosophy, beautiful but untethable to the physical world we can observe and measure. Loop quantum gravity offers a different path toward unification, one that begins with the radical proposition that space-time itself is not continuous but discrete, built from tiny, indivisible units of geometry. Imagine zooming into the fabric of space itself, deeper and deeper, until you reach a scale where space and time lose their smooth character and become grainy, pixelated like a photograph viewed under extreme magnification. At this fundamental scale, space consists of tiny loops of geometry, connected in a vast network that gives rise to the smooth space-time we experience at larger scales. In this picture, the very concepts of distance and duration become quantized, existing only in discrete packets. There is a smallest possible length, the Planck length, and a shortest possible time interval, the Planck time. Below these scales, the familiar notions of space and time simply cease to have meaning. This radical reconceptualization resolves some of the infinities that plague attempts to quantize gravity, suggesting that the apparent contradictions between quantum mechanics and general relativity arise from our mistaken assumption that space-time is infinitely divisible. The implications of loop quantum gravity extend far beyond the technical details of theoretical physics. If space-time is indeed quantized, then the universe itself might be thought of as a vast cosmic computer, processing information at the most fundamental level. The Big Bang, in this view, might not have been the beginning of time, but rather a moment when a previous universe, collapsing under its own gravity, reached maximum compression and then bounced back, creating the expansion we observe today. This Big Bounce scenario eliminates the troublesome singularity at the beginning of time, replacing it with a moment of maximum density followed by expansion. Perhaps the most mind-bending proposal to emerge from the quest for quantum gravity is the holographic principle, which suggests that all the information contained within a volume of space can be encoded on its boundary. This idea emerged from the study of black holes, those mysterious objects where gravity becomes so strong that not even light can escape. Stephen Hawking's discovery that black holes emit radiation and gradually evaporate led to a profound puzzle. What happens to the information that falls into a black hole? Does it disappear forever when the black hole evaporates, violating the fundamental principle that information is conserved in quantum mechanics? The holographic principle offers a startling resolution to this paradox. It suggests that the information falling into a black hole is not destroyed, but is instead encoded on the black hole's surface, its event horizon. Just as a hologram can store a three-dimensional image on a two-dimensional surface, the black hole's surface contains all the information about its interior. But the principle goes further, proposing that this holographic relationship is fundamental to all of reality. Every volume of space, every three-dimensional region, might be nothing more than a holographic projection of information stored on its boundary. This leads to the extraordinary possibility that the three-dimensional world we experience, with its depth and volume, its particles and forces, might be an illusion, a shadow cast by a more fundamental reality existing in fewer dimensions. We might be like characters in a cosmic movie, thinking we exist in three dimensions while actually being projected from a two-dimensional screen. The implications challenge our most basic assumptions about the nature of reality, space, and existence itself. Current experiments at the Large Hadron Collider continue to probe the high-energy frontiers where quantum gravity effects might become detectable. Scientists search for signs of extra dimensions, for evidence of string resonances, for any hint that reality extends beyond our current understanding. Gravitational wave detectors like LIGO and Virgo offer another window into the quantum nature of gravity, measuring ripples in space-time itself with unprecedented precision. These experiments might reveal signatures of quantum gravitational effects, providing the first experimental evidence for theories that until now have existed only in the realm of mathematical speculation. The quest to understand quantum gravity is more than an academic exercise. It addresses some of the deepest questions we can ask about existence itself. What is the nature of space and time? Are they fundamental features of reality, or are they emergent properties of something more basic? What happened at the very beginning of the universe? What lies at the center of a black hole? These questions touch the very foundations of what it means to exist in a physical universe. As we drift towards sleep tonight, we can find comfort in the knowledge that some of the brightest minds in human history are working to unravel these mysteries. They labor in the quiet hours, filling blackboards with equations, building mathematical bridges between the quantum and the cosmic, seeking the hidden harmony that might unite all the forces of nature into a single, elegant theory. Their work reminds us that the universe is not just a collection of objects moving through empty space, but a deep, mysterious symphony whose most beautiful movements are still being composed. In the gentle darkness that surrounds us, we can imagine ourselves as part of this cosmic composition, patterns of quantum information dancing in the holographic projection of space-time itself. Whether we are made of vibrating strings in higher dimensions, or quantum loops of geometry, or holographic shadows on a distant boundary, we remain connected to the deepest mysteries of existence. The same quantum gravity that might have sparked the Big Bang and that warps space-time around black holes also flows through our own bodies, binding the atoms that make us to the fundamental structures of reality. In seeking to understand quantum gravity, we seek to understand our own deepest nature, our place in the cosmic dance between the very small and the very large. Now we will discuss Chapter 10, The Quantum Nature of Reality. What it all means. As we reach the final chapter of our gentle journey through the quantum world, we find ourselves standing at the edge of one of the most profound questions ever asked. What does quantum physics actually tell us about the nature of reality itself? Throughout our exploration, we have encountered mysteries that challenge every assumption about the world we thought we knew. We have seen particles that exist in multiple states simultaneously, connections that transcend space and time, and a universe that seems to respond to the very act of observation. Now, in this quiet moment before sleep, we must ask ourselves what all of this quantum strangeness means for our understanding of existence itself. The story begins with a revolutionary idea that emerged from the depths of 20th century physics: the notion that information, not matter, might be the fundamental building block of reality. This concept, elegantly captured in physicist John Wheeler's phrase "it from bit," suggests that what we perceive as solid, substantial reality is actually composed of pure information. Every particle, every force, every interaction can be understood as patterns of information processing. In this view, the universe is not a vast machine made of gears and springs, but rather a cosmic computer calculating its own existence, moment by quantum moment. Consider how strange and beautiful this perspective becomes when we examine it closely. The electrons spinning around atomic nuclei are not tiny spheres following predetermined orbits, but probability clouds of information, defining where they might be found when observed. The photons carrying light from distant stars are not particles or waves, but packets of information about electromagnetic fields propagating through space. Even the vacuum of empty space, which we once thought of as nothingness, reveals itself to be a seething ocean of virtual particles, constantly appearing and disappearing, carrying information about the quantum fields that permeate all existence. This informational view of reality helps us understand why quantum mechanics is so deeply concerned with measurement and observation. When we measure a quantum system, we are not simply uncovering pre-existing properties, but rather extracting specific information from a realm of pure possibility. The wave function collapse that occurs during measurement is not a physical process happening to material objects, but an informational process where definite answers crystallize from indefinite potential. In this sense, every measurement is an act of creation, bringing one specific reality into existence from among countless quantum possibilities. The implications extend far beyond the laboratory. If reality is fundamentally informational, then consciousness itself might play a more central role in the universe than we ever imagined. Some interpretations of quantum mechanics suggest that consciousness is not merely an emergent property of complex arrangements of matter, but rather a fundamental feature of the informational substrate from which reality emerges. In this view, awareness and existence are intimately intertwined, with consciousness serving as the mechanism by which pure possibility becomes actual experience. This brings us to one of the most profound insights of quantum physics. Reality appears to be process rather than substance. The classical view imagined the universe as composed of solid, enduring objects interacting through forces across space and time. But quantum mechanics reveals a different picture entirely. What we call particles are actually dynamic patterns of activity in underlying fields. What we call forces are exchanges of information between these field patterns. What we call objects are temporary stabilizations of quantum processes that are constantly fluctuating and evolving. In this process, view of reality, nothing is truly static or separate. Every quantum field extends throughout all of space, connecting every point to every other point through invisible correlations. The phenomenon of quantum entanglement, which initially seemed so mysterious and troubling to Einstein, becomes a natural consequence of this fundamental interconnectedness. When two particles become entangled, they are not creating a new connection across space, but rather revealing the deeper unity that was always present beneath the apparent separation. Time itself takes on a different character in this quantum worldview. Rather than being the stage upon which events unfold, time becomes one of the patterns that emerges from deeper quantum processes. Some interpretations suggest that the flow of time is not fundamental, but rather an emergent property of how information propagates through quantum systems. In this view, the universe does not evolve through time so much as time evolves through the universe, arising from the accumulation of quantum measurements and the increasing complexity of information patterns. The role of complexity becomes crucial in understanding how our familiar classical world emerges from quantum foundations. Through a process called decoherence, quantum systems interact with their environments in ways that effectively select certain possibilities while suppressing others. This is not a violent collapse of the wave function, but rather a gentle settling into classical behavior as quantum information becomes entangled with the vast complexity of the surrounding world. In this way, the deterministic, predictable realm of everyday experience emerges naturally from the probabilistic, mysterious realm of quantum mechanics. Yet perhaps the most beautiful insight of all is how quantum physics suggests that the universe is inherently creative. Unlike classical systems, which simply rearrange existing components, quantum systems generate genuinely new possibilities through their interactions. Each quantum measurement creates information that did not exist before. Each entanglement weaves new patterns of correlation into the fabric of reality. Each moment of conscious observation participates in the ongoing creation of existence itself. This creativity extends to the deepest levels of physical law. The constants that govern quantum interactions, the speed of light, Planck's constant, the masses of fundamental particles, appear to be finely tuned to allow for the emergence of complexity, consciousness, and life. Whether this fine-tuning is the result of selection from a vast multiverse of possibilities, or whether it reflects some deeper principle of cosmic creativity, remains one of the great open questions of our time. As we drift towards sleep on this gentle tide of quantum contemplation, we might reflect on what it means to be conscious beings in such a universe. If reality is fundamentally informational, then our thoughts and perceptions are not mere shadows cast by material processes, but active participants in the universe's self-creation. Each moment of awareness, each flash of understanding, each dream that carries us toward rest becomes part of the cosmic conversation through which existence knows itself. We are not separate observers standing outside reality looking in, but patterns of consciousness arising from the very quantum processes we study. We are the universe becoming aware of itself, cosmic information processing systems capable of reflecting on their own nature. In this sense, the mystery of consciousness and the mystery of quantum mechanics are intimately connected, both pointing toward a reality that is far more participatory, creative, and alive than classical physics ever imagined. The quantum nature of reality whispers to us that existence is not a problem to be solved, but a mystery to be lived. We are temporary patterns of organization in the quantum field of all possibility, brief eddies of awareness in the cosmic flow of information and energy. Yet in our brief flowering, we carry within us the capacity to wonder, to question, to seek understanding, and to find beauty in the very strangeness of existence itself. And so, as this final chapter draws to a close, we are left not with answers, but with a deeper appreciation for the questions. Quantum physics has not solved the mystery of reality. It has revealed that reality is mystery itself, an ongoing process of creation in which we are privileged to participate. In learning to embrace this uncertainty, this openness, this fundamental creativity at the heart of existence, we discover that we are not lost in a meaningless cosmos, but intimately woven into a universe that dreams itself into being through our very capacity to wonder about its nature. Sleep well, my friend, knowing that you rest within the quantum heart of a reality more beautiful, more mysterious, and more alive than we ever dared imagine.